From one theme of statistical science, we will move on to an entirely different spectrum of statistical science. Uh, Please reserve all your questions for the Q&A after the talk of the next speaker. Or alternatively, you can type your questions in the Q&A box. We will read it later on. So our next speaker started from UP Los Baños for his BS and MS statistics degrees. He then proceeded to pursue MS and PhD statistics at Florida State University under the supervision of Miles Hollander. He is currently professor at the Department of Statistics, University of South Carolina. He also served Bowling Green State University and has visited University of Michigan. He is a fellow of American Statistical Association, elected member of ISI, and current vice president of PAASE. Quick trivia for our users here. He actually contributed the packages GCMREC, SURVREC, and GVLMA. Maybe there are additional packages now as he delivers his talk. He will talk about Poisson and Over-Dispersed Poisson Regression models with application in forecasting COVID-19 death. So by the way, he just updated his slides early this morning to account for the recent data on COVID deaths. Please welcome Professor Edsel Peña.
Thank you, Arnel. Do you see my slides?
Yes.
You can see it. Okay. So thank you very much, and thank you, of course, for Gisela, her tireless efforts in organizing this symposium conference during this pandemic. It's very admirable, and it's nice that we could see everybody in the statistics community who are in Europe, the US, in the Philippines, and I've heard a lot of the other people there. Dr. Mariano Pilino Lansigan was my professor, Ani Runelia was my advisor in Los Baños, and then Grace and I were together in Bowling Green State University before we left Bowling Green. So, and of course, Reniel, I know from UP Diliman. So my talk actually is not too complicated. It's actually quite simple, and this actually started when the pandemic started. I was teaching an undergraduate engineering class in statistics, and then I was also teaching a graduate class in stochastic processes. And because of course we all have to do things online, I started using this as a motivation. Every class meeting, I update the data and I pose the statistical question. I say, how could you predict how many deaths is going to be 15 days from now? Something like that. So of course, in the beginning, it's very difficult to do that because you don't have much data. But as time passes by, the simple methods that we were using was not working well at all. They were not working because they're too simplistic. And so it became a challenge to me. I said, how do you do this? And Ben Lieberman was a student in my stochastic process class, and I was teaching them the continuous time Markov chain. And that is one possible model, compartment models. And then George Sluta is a professor at Georgetown. I met him in January when I gave a talk in Georgetown. And he said, let's collaborate on something. And then the pandemic hit, so we decided that we should collaborate on something about the pandemic. And then Tayo Kim was my former PhD student. He's now a postdoc at University of Haifa in Israel. And so we gathered together online. We didn't meet at all, of course, for the past 3 to 4 months. And then we ended up with this paper. And we deposited the paper in the archive 2 weeks ago, or maybe 1.5 weeks ago. So it's the one that is contained in the bottom part there. So you could easily search that. Okay, but here's the motivation. So the European CDC, that's the European Center for Disease Control, publishes this data updated every day. This is for all the countries in the world, okay? It publishes the number of cases, the number of deaths daily, as well as cumulative. And so here, for instance, I put the one for USA, and this is until July 18th, when I first completed a version of the paper. The left plot there is the daily deaths. Okay, so this is the daily deaths, and you notice, of course, that things are increasing again by 7/18, and that could be because of the social easing that was happening. And then on the right plot here, that is the cumulative deaths. As time passes by, it's the cumulative deaths. So here, looking at this picture, for instance, you could ask, what will be the total number of deaths in the USA by August 1, based on this data that we are seeing? How do we do that prediction? So that's the basic motivation. And you could do that for many countries that you're interested. In particular, for instance, this is the data for the Philippines. And you notice for the Philippines, there's this big outlier which could mess up potentially whatever you do in prediction. Okay, so the program that we have, you could pick any country and then you could actually do that. So but that's the basic motivation that we have. So the question then is, given this type of data, if I wanted to predict or to forecast the number of deaths, total deaths at a certain time, how do I proceed to do that? Okay, so that's the basic motivation. And why is that important? Because it's important, of course, because it could decide whether we should go back to social distancing. It could decide whether we should open universities or school this fall. It could decide whether beaches and the businesses should be open or closed. So these are very important ones. It could decide the election in the US, for instance. Okay, and but it also leads us to some very interesting statistical questions that are outside of the pandemic that could be utilized in economics, in physics, for instance, in geophysical studies like the ones that I listened to the other day about earthquakes in volcano eruptions. Okay, another thing is that we'd like science to be believed by people. And if the forecasts that we are providing to society are bad forecasts, then the belief or the trust on us will start eroding. They'll say, why should we believe you? Your forecast was quite bad a month ago, something like that. So it's a very important issue that we have to consider. Now, when you think about this problem, I said, how do I explain this? You actually have to start thinking about a very simple experiment. In this, the experiment of tossing a coin. You might say, how is this pandemic related to tossing a coin? Okay, and here's the idea. Let's imagine that you have a biased coin and the probability of landing up head is equal to theta. If you toss this coin n times, and then you denote by y the number of times that the head occurred, then we know from basic statistics that y has a binomial distribution with parameter n and theta. So the mean is n theta, the variance is n theta times 1 minus theta. Okay, so this is what we know from our very basic statistics. Okay, the standard deviation is the square root. Okay, now, so here are three shapes of binomial probabilities. I think the first one is a 50-50 chance. The second one is a 30% chance for heads. And then the last one is 10% chance for heads. And you notice that it gets shifted and then you get some skewness as you move to lower probabilities of header. Okay. Now, one of the things that we study from statistical theory is that if you let n, number of trials increase, but you also let theta n, the probability of a head, decrease, but you keep the mean the same as you change n. So you set that to be equal to lambda. And then you let n go to infinity for this binomial probability. It will converge to what we call as the Poisson probabilities. Okay, so, and these probabilities here are what we call as the Poisson probabilities. And what we have done there is to let theta sub n go to 0. So technically, the probability of an event, which in this case is head, is going down to 0. So it becomes rare. So as a consequence, these Poisson probabilities are models for what we call as rare events. Okay, and here's the basic definition of a Poisson probability function. Okay, so I'll denote it as POI lambda. In the lambda is the rate, which is the mean, and it is also the variance. So the standard deviation is equal to the square root of lambda. So it's a very, very important probability function, but that's simply coming from the binomial distribution as a limit, okay? And here are three shapes that I put here for the Poisson probability function. The first one is when lambda is 0.5, so you have very high skewness. The second one is for lambda is equal to 10, and then the next one is for lambda is equal to 30. And we have here from the central limit theorem that if you let lambda increase, if lambda is large, then you actually have an approximate normal distribution. And that's coming from the central limit theorem. Now, the Poisson model is very important because it models general rare events, earthquakes, volcanic eruptions, house fires, vehicular accidents, fights between husband and wife. That's also a Poisson distributed random variable. Getting a perfect score in standardized tests, assuming that there's no cheating going on there, that's going to be a Poisson distributed thing. Winning a lottery, that's a rare event. Getting a paper accepted for publication, that's a rare event too. And of course, getting infected by the SARS-CoV-2 virus and dying from COVID-19. These are rare events. And as a consequence of that, the Poisson distribution is a good model for these rare events. That's why somehow the Poisson must come into the picture when we are trying to analyze these COVID-19 deaths, okay? Now, so the basic problem that comes up then is this. I have to start with. Let's suppose that I have a random variable that has a Poisson distribution with parameter lambda, okay? What you would like to come up with is a subset of the set of integers, I'll denote that by gamma, such that the probability that y sub 0 belongs to that subset is at least equal to 1 minus alpha. I'm assuming for the moment that lambda is known. If you have that subset, okay, then you would call that subset as a 100 times 1 minus alpha percent prediction region. Okay, it's like the prediction region that we have in normal models, okay? But here you are dealing with a Poisson random variable, okay? Now, of course, if you have a prediction region with a certain prediction level, like 95%, you would like it to be as small as possible, okay? Because large prediction regions will be useless to us. It doesn't tell us much information. So you have to set your level, and then you want to make it as small as possible. So that's what we would like. Now, why do we want prediction regions? It's because if you simply give point predictions, like you say, the number of deaths is going to be equal to 100,000. You know that that prediction is not going to be right. You could never be 100% correct about that. So what you would like to do is to have a degree of confidence on that region, the amount of size of that prediction region. That's why prediction regions are more useful than point predictions, because it provides us the degree of precision as well as the accuracy of the forecast that we are providing, okay? But we would like that to be as small as possible for a given level, okay? Now, when lambda is known, okay, you could actually obtain the very best prediction region that you could have, okay? And this is given by this weird looking formula, okay? It's the union of several sets, but the basic idea there is actually the idea behind the Niemann-Person lemma in hypothesis testing. You could use the calculus of variations to come up with the shortest prediction region that you could have for a given level of confidence. And that is provided by this. And that's not very difficult to compute, but what I want you to see here is how you actually obtain that. And the basic idea is this. If you have the Poisson probability function that is provided by this plot here, what you're basically doing is you're cutting it at a certain level, okay? And you cut it at a certain level such that the probability inside here is close to that confidence level that you would like. So if you wanted 95% confidence level, you set that such that this total probability is 0.95. Of course, sometimes you have to do randomization to get exactly the 95% level. Like in the Niemann-Person lemma, you usually have that gamma, which is the randomization. And that's provided by this part here. But basically, when the lambda is large, that randomization is not very critical. But this is the picture of how you obtain the best prediction region that you could have, okay? Another way that you could do that, and I think this might be familiar to many of us, is simply to use the normal approximation. Y sub 0 is approximately normal with mean lambda and variance lambda. So you could standardize and you get this approximate standard normal. You could then use this as a pivot for Y of 0. And then when you do that, you obtain this prediction region. Okay, but that is when lambda is known. Okay, now that's not the important one though, because the important one is the situation when lambda is not known. Okay, so how do we deal with it? Okay, now if you don't know lambda, then you must have a way of estimating lambda. So what we do here then is we assume that we have a random sample or training data, y1, y2 up to yn, that came from that Poisson distribution. And then the goal is to construct prediction region for an unobserved y0 that also has a Poisson distribution with parameter lambda. How do you do that? So the idea is very simple. You say, okay, I'm going to observe y1 to yn. I could then estimate lambda. And then having estimated lambda, I could plug that estimate into that prediction interval that I presented when lambda is known. How do you estimate lambda? You could use maximum likelihood, or you could use method of moments, and that simply leads you to the sample mean as the estimate of lambda. So this is your estimate of lambda. And then, as I've said, the intuitive thing to do then is you say, I'm going to plug in that lambda into lambda on these two prediction regions. And I say, oh, that's quite intuitive and reasonable. And I say, isn't that? Okay. The problem though is that it is actually a faulty strategy. Why is that faulty? Because if you simply plug in this lambda hat into these prediction regions, you did not take into consideration the induced variability in the estimation of lambda. So what you will get is if you simply do that, you will get narrow intervals instead of proper intervals. So if you get narrower intervals than what you should have, then the confidence coefficient that you had set, like a 95% confidence, will actually be lower. And so you are not satisfying the guarantee that you are providing your users. So you have to do something else, okay? And how do you do that? So what you need to do then is to try to correct for the estimation of lambda. And there are several strategies. I'll mention here two ways. One of them is to use a second order Taylor expansion, and then to adjust the pk after you had estimated it by lambda. And this is one way. The other way is to simply use a normal approximation, but to take into consideration that you had estimated lambda. And what you have to do there is to use the delta method. And when you do that, you obtain this prediction interval, okay? So again, this still looks familiar, okay? Because of the correction there, okay? This one is a little bit more complicated. And in fact, this one did not turn as well as this one for large lambda. But these are ways of doing that. And you could examine the performance of these different prediction regions. And here actually the three that I mentioned will be the black one, the blue one, and then gamma 3, which is the pink one, okay? And these are the level for different sample sizes and for lambda equal to 5 here. And I think the gamma 1 there is the one that is based on the normal approximation. That seems to perform best in this situation. And then the second plot here pertains to the width of these prediction intervals. You would like that to be short. The black one, which is the one based on the exact prediction interval, where you simply replace lambda by lambda hat, has the best length, except that it suffers in terms of the confidence coefficient, because I didn't adjust for the estimation of lambda. But basically, the one based on the normal approximation ended up best in that type of situation. Okay, now that's the situation, and this is for n lambda is equal to 30, same type of conclusion. Now that's the situation though, where I only have one Poisson distribution. Okay, I only have one lambda. That's not the situation when we are dealing with a pandemic, because for the pandemic, what you actually see are the deaths, daily deaths for different days. Okay, like the picture that I have shown here, this is the data that we are seeing. So it's not right to assume that they have all the same parameters. So how do you deal with that then? Okay. So the way we dealt with that is that we used the number of days since the beginning, which is 1231, as D, variable D. And then we also categorized that day into 0, 1 to up to Sunday, depending on what day that is. And what we assume then is that the number of deaths, daily deaths on day D, has a Poisson distribution with rate that depends on that D in the day. Okay, and so this is the model that we are considering, and this is what you call as a Poisson regression model. Okay, as compared to the earlier one, we have now here predictors, and you call this as the Poisson regression model. Okay, in the cadre is the order. Okay, so it's a polynomial basically, but you could use some other basis function for this one. Okay, so you have this situation. Okay, I think that was my timer, but I might have. Okay, so now, so you have this data, and then you fit that then. Okay, and you could do the fit for. You could estimate the theta parameter, which are the coefficients, using maximum likelihood. Okay, and then from maximum likelihood theory, we know that the estimator is going to be asymptotically normal with mean theta and then the inverse of the Fisher information. Okay, Fisher information is the negative second partial derivatives of the log likelihood. Okay, and as a consequence, if I wanted to predict the value of daily deaths at D0, a future day, okay, I could use again the idea that I had earlier, but now in a more complicated fashion. Again, I'm going to use the delta method, and then when I use the delta method, I come up with this prediction region or interval. Actually, you could just remove that, and then that is a prediction interval. Okay, so it's much more complicated because, of course, you have matrices now here, but the principle is the same. That's how I presented the case without the covariates. Now, so I said, let's apply this idea then to the COVID data. And then this is an application for, I think, until May 15th, when we were in the middle of this research. And so we apply this prediction region. But then what you would notice for this prediction region is that there are still a lot of points that are outside. That shows somehow that the model is not right, that there is over-dispersion. Because if the model was correct, there shouldn't be many points outside of these prediction regions. Okay, so we knew that something went wrong, and I was very concerned about that because I was showing this. I said this model is not working properly. So we have over-dispersion. So why could there be over-dispersion? It could be because the reported daily deaths are getting perturbed. Okay, there could be lack of personal or certain days. So consequently, people are not there to report things. It could be that the definition of what COVID-19 death really means, so it keeps changing. It could be gaming of the system. It could be excess deaths due to other causes, or maybe causes that are not getting attributed to COVID-19. And of course, as just the other day had mentioned, all models are wrong, but some are useful. Okay, so what we did then is we said, what could we do to correct for this over-dispersion? And it's not technically over-dispersion at the point 0. It's we usually zero inflated models. It's not that way. So I keep thinking about this, and it turns out that we could borrow an idea from survival analysis, frailty models. And what you basically do is you assume that you have an underlying hidden process, which is Poisson. Okay, that's the Y star. And then you have a latent variable, CD, which you don't observe. Okay, that has a gamma distribution with scale parameter and shape parameter psi. So the mean is 1, and then the variance is 1 over psi. And then you assume that these are independent. Okay, and then the observed process, the one that you are seeing, is a perturbation of that Poisson variable perturbed by the CD, and then you take the integer because you have integer values here. Okay, so now when you do that, you actually get an over-dispersed model. The mean is still approximately the same as the original, but the variance is now larger than under the usual Poisson regression model. In the Poisson regression model obtains when you let psi go to infinity. So you have a bigger model here then, with a Poisson regression model obtained as a limiting model in this situation. So this is the basic framework for that, okay? And you could then estimate theta psi using C estimation. It's hard to do the maximum likelihood because you don't have a closed form. So you could use C estimation or M estimation. And then you also have the duty for this, okay? And here you get what you call as a sandwich estimator because you're not technically using the MLE. But this sigma is still the Fisher information in that situation, okay? But this need not only simplify to sigma inverse. And you could estimate this covariance matrix consistently, okay? Now, because of that asymptotic, okay, you could then come up with a pivotal quantity again for Y0. And then this is the pivotal quantity. From this pivotal quantity, I could then flip that to come up with a prediction region, approximate prediction region for the number of daily deaths at D0, and that is given by this, okay? It looks complicated, but it's not really that complicated. There's some inversion that needs to be done here, so that's where the computational thing comes up. But it's kind of still simple, following the principle that I had earlier. So we apply this to that data that I had earlier, and then how you notice that the prediction interval actually covers the observed points, okay, as compared to earlier when it wasn't covering many of the points there. So somehow this tells us that this is okay. And then the degree that we used here is 5. So 5-degree polynomial with respect to the day number. And then of course the day also was there. And that the data was until May 15, okay? Now, but predicting the number of deaths per day is not the most important one. We would like the cumulative deaths. So how do we do that, okay? So why is this important? Because this could impact behavior. If the cumulative deaths is increasing too quickly, people might say, I'd better wear a mask. Maybe Trump will suddenly decide that he should wear a mask. People could decide who to vote because of the number of people that are dying, for instance, okay? And so the idea that we had done here, although I could now improve this today, but I will stick with this. The idea is that if it is today, what you could do is to predict the number of daily deaths for the days that are coming forward, create the intervals there, and then simply add the lower bounds, simply add the upper bounds for those, and then overall you get a total. And when you do that, that provides you a conservative prediction interval for the day that you are interested. It's conservative because you might be interested in 95% prediction interval, but you are actually getting 99%. So you're sacrificing a lot, but at least you are guaranteed that you are obtaining the correct interval, okay? So that's the basic idea. But today, or actually this week, we got an improvement over this that gets us another one because we didn't use this CDAC corrected ones. We obtained a more direct one, but it's not covering that in there. Now, so these are now plots only, so I'll be done in 1 minute here. So this is the application to the COVID data. And then this is from, I used the data until July 5. And I'm predicting until July 20. I think this is when I started preparing the slides. So the data that I used is up to here. And then the red ones there were the subsequent observations. So you notice that the prediction interval covered almost all these points. Actually, it covered all the succeeding observations. Okay, so everything seems to be fine. And then this is for the cumulative ones. For the cumulative ones, you notice that there was degradation at the end, and I think that was because of the social easing. So that the model, the data that I used did not take into consideration. But you notice that it's still quite good in this prediction interval at 720. So because I was looking for today, I look at the prediction for August 1 using data up to July 15. And then this is the data is here. These red dots here are the predicted daily deaths. You notice that they're quite good actually in terms of the fitted prediction curve there, and so on and so forth. You might say, why is this wiggly? Because the day effect is actually significant, okay? The highest daily deaths that are getting reported are on Tuesdays, Wednesdays, and Thursday. And that's quite puzzling. But what happens that on Sundays, in Saturdays, people I think are not in the hospital, so they do not report as many deaths as they could. Okay, but that was significant, and that's why you have this wiggly thing here. And then for the cumulative deaths here, you notice that from 715, these are the subsequent observations. The blue line there is the predicted curve. So almost all the points there are very close to the predicted curve. But of course, the prediction interval becomes wider and wider as you go farther and farther away. And today, so what I did is, that's the one that Erniel was mentioning. I run it today, so the last pointer is 726. And then I also did, what's the prediction if I use all the data until today and until August 1. And then these are the no red curves there, points, because I don't have those data yet. But that's the predicted curve there. And then this is the predicted for the cumulative. Okay, notice that, of course, since I'm closer to August 1, you have a narrower prediction interval. Okay, so it seems to be working. What we have to see, there are still problems, especially when you want to do long prediction. So there's my concluding remarks. I only use daily deaths here, okay? Why not other feature variables? Okay, so you could, but you have to be careful also there. Why not a longer forecasting horizon? And you recall Donald Rumsfeld, known knowns, known unknowns, unknown knowns, unknown unknowns. So you could have adjusted numbers, social distancing, easing, all these other things that could have an impact on the data. And then there's also the feedback loop. Whatever the government does, it could affect the consequent number of deaths later, okay? And then of course, there's the problem of extrapolation, okay? I say actually that COVID-19 deaths forecasting is as dangerous as the disease if you're a statistician. And then I mentioned, of course, Niels Bohr. He said that it is difficult to make predictions, especially about the future. And in this COVID forecasting, you immediately know in a few days if your forecasts are good or bad. Okay, and that ends it. And just wanted to thank again Gisela for her really tireless effort in organizing this. Erniel for inviting me to his session. I get to meet other statisticians. And of course, it's very nice to see Grace Montepiedra. I think I saw her last in 1996 maybe, and so on. And to all the people that are here, thanks for listening. So I might have exceeded time, Erniel. Thank you.
Okay, thank you very much, Edsel, for the very interesting talk. Now,